Hello and welcome back to Calculus 1, section 4.4, optimization. What do we want to know? We want to know the maximum profit and the minimum cost and maximum volume and minimum surface area and a whole bunch of things that are very useful in engineering, very useful in business, economics, and so on. So this is another one of the sections that is applied and that you can directly use to make money. Is anyone in that packaging engineering program that has? Because we partnered with the university, right, for that thing. Packaging engineers are getting hired apparently before they even graduate because there's a huge need, which is the reason why we have a track over here to transfer students into the field. What do? They create boxes and packages for the products that need to be shipped halfway across the world because all of our manufacturing is where? Not here, exactly. So, you know, you want to minimize the surface area of the box, because if you are minimizing the surface area of the box, you are using the least amount of material to make the box, i.e. you are saving on cost because you lose less materials to make the box. Now this is where business comes in. Now, if you are making, now some of you would say, yeah, what's the big deal? You save 10 cents. Sure, you save 10 cents on 100,000 boxes, right? And then you have a different product line and a different product line. So, right. So there is a huge application for this particular section for you to directly start making money tonight, actually after the class. There was a posting for immediate hire at the Exxon Research building in Clinton for optimization and data something. But yeah, it's this. Lots and lots of jobs of optimizing the production lines and everything else. So pay attention, right? Don't worry about the grade on this one. This is the one that makes you money if you have, you know, any sense of what the work is or means. So let's start by the simplest possible problem, just to introduce the concept and the steps involved in getting these problems done. So say that you say sum of two numbers is, I don't know, is 36, okay? Which two numbers will give us maximum product? So what am I looking for? I'm looking for two numbers, x and a y, whose sum is 36 and the product is maximum. I can pretty much guess anything, right? Shall we just say 1 and 35? Right? If you want to guess this, go ahead. Clearly, if you do 36 plus 0, right? 36 plus 0 in a product is going to give you 0, so that's not going to work, right? But how about you guess 1 and 35? Because 1 plus 35 is 36, and if you multiply 1 times 35, you get 35. 35 is solid. I don't think you will complain much if you found 35 bucks on the street, right, walking around. But then, one is going to suggest what? Well, let's see. How about you suggest 2 and 34? That will work. So 2 plus 34 is also 36, but 2 times 34 is 68. Wow, 68 is much better than 35. So, right, and you get to continue this trend. Yeah, and you have to guess. So is there a way to actually use calculus to solve this quickly? And the answer is clearly yes. I'm going to create two equations. One equation is going to be called constraint, and the other one objective. Constraint equation, just read its name, right? You are working under constraint that your sum has to be 36. Can we agree that the appropriate name is constraint function? And what is your objective? Your objective is to actually have the product be a maximum. So you translate the sentences given to you into formulas directly, one by one. The first sentence says sum of two numbers is 36, x plus y, a plus b, whatever. And the second sentence says the product of numbers should be max, right? And now you have two equations and two unknown values. Well, we can solve that, right? The issue is that we have this max over here, which kind of spells, yeah, maximum, critical point, derivative, right? All of that good stuff. So what's the procedure and process? You will always solve for one of the variables in a constraint and plug in the objective to kill off a variable. Y equals 36 minus x. Plug in. So we get x times 36 minus x. Distribute x. And now, when you have a single equation with one variable, hit this with a derivative. What's the derivative of 36x? Thank you. And what's the derivative? Okay, so who's usually not coming to class? Because I'm apparently allergic to that person. Who? All right. Out. For some reason I can't speak. And it has to be allergy to someone. I'm not allergic to food or plants or anything like that, but definitely people. No offense, okay. I've been teaching in this classroom for centuries now. I'm ancient, like Yoda. No, wait, Daniel, you're the one who's usually missing. Oh, yeah. Yeah, whoever it is, just leave. And then minus 2x, right, on a derivative. Now, what's the derivative of maximum? 0, right? Why is the derivative of maximum 0? Well, or minimum later on. Because look what max is. Aren't these numbers here, right? It's a constant. So the derivative of whatever this is, area, whatever, is always going to be 0. So the derivative of max is 0. Now, doesn't that also very nicely line up with the fact that you, in that first section, set your derivative to 0 to find min and max, right? Yeah, right? So you see how now all of that stuff actually comes together. We didn't set this equal to 0. We derived that it's equal to 0, and we know from theory before that it should be equal to 0 when you're looking for min and a max. Solve this equation, and there's your x. And then go back to the other equation to get y, And every single problem in this section is this. Two equations combined into one, hit it with the derivative, and that's done. So we all see that x is 18. Plug in. Y is 36 minus 18. Y is 18. So answer is x equals y equals 18. So what are the two numbers whose sum is 36 and product is max? It's 18. If you try anything else, product will be less than a max. Now go ahead, go 18 times 18, and you will find what the maximum product is. So, yeah. Why would, no. You move 2x to the other side.
Oh,
yeah. Is he being mean? Yeah. Is he being mean? I'm trying to fish it out, man. Why do you have to ruin it? Why do you have to ruin it? He was safe from throughout the whole conversation. All right. So let's put this into perspective now. I should really change the title of this into Farmer Troubles. So what do we have? See, this farmer has 2,000 feet or yards of fence on a pile. All right? So, farmer has 2,000 yard of fence. He wants to fence off a rectangular area. So he wants to fence off a rectangular area. No. He wants to fence off a rectangular plot of maximum area. There we go. Find the dimensions. You get the idea. Hey, you got everything you need. You know the geometry. What's the geometry of the problem? Rectangle. If he wanted to fence off a triangular area, it will be a triangle, right? We don't usually fence off triangular areas, but we can get creative. So we already know that the geometry of the problem is a rectangle, and rectangle is going to have x and a y on the sides. Where do you put area? Where do you put fence? At the perimeter, also known as the perimeter fence, right? For that reason. So the black line you see is actually the bird view of the fence. It fences off the rectangle inside so that the zombies can come in. So, good. So what would be my two equations? What will be my two equations?
X times y equals max.
Very good. That's the second one. X times y equals max because I want the area to be maximum. That's the objective equation. Objective function. X plus y. You don't want to fence off this area here, just half? What happened? Beautiful. 2x plus 2y. That's the perimeter of the rectangle. So 2x plus 2y equals 2,000. You are going to use all 2,000 yards of fence to go across. So if it's going to help here, x's and y's all around. And this is your constraint function. Great. Solve it. Divide the upper equation by 2. Make it easier. And then solve for y as 1,000 minus x. Plug in. And we have x times 1,000 minus x equals the max. One thousand x minus x squared is equal to a max. And this is where we hit this with the derivative, because we want to find the critical point at which the max occurs. So we have 1,000 minus 2x equals 0. Derivative of a max is 0. And x is 500 yard. Plug in. Y is 1,000 minus 500. Y is also 500. And we have 500 by 500 yard square. That guarantees maximum area. So, constraint equation is that all of the fence you have is 2,000 yards. There's no more. You have 2,000 yards of fence, and you want to use all of that, and you are working within that constraint. Does it make sense when you use the words and language, right? You have a constraint that you can use only up to, right? And you're putting that fence on the perimeter, so it should be quite clear that it's the perimeter that you will be using. You want the maximum area, therefore x times y is a max. And the rest is solving. You solve constraint equation for one of the variables, plug into the objective equation, work out the algebra, hit it with the derivative. Now it's equal to 0. We are looking for min-max at that point. You get 500. So find the y value, and then you have your answer. Problem solved. So this is the entire problem. What I'm going to do now is I'm going to modify it a little bit. It's the same farmer problem, except now the plot of land is adjacent to this river. Should put some salmon in here, right? There's salmon for you. It's not good salmon? Oh, carrots, okay. Carrots are in the water, nice. How about now? Chopped up carrots? Okay, fine. The most important, well, oh, okay, if the salmon is swimming to the left, which way the water goes? Right. Every time, I love it. No, depends on the time of the year. Yeah, they come back. Yeah, some of them don't come back, exactly. It's not fun to be salmon. If you don't end up eaten by a bear, you end up eaten by me, so, yeah. Had salmon yesterday and the day before, so there you go. They have a lot of natural enemies, and if I'm your natural enemy, it's not good. Right? No. It's always some of them, right? These are the ones that survive and coming back, okay? Guys, we have the same amount of fence, 2,000 yards. Is anything different now? Only 1x. You see? So now your constraint function is different. All right, let's go. Now constraint function is x plus 2y equals 2,000. And my xy area is still max. So the same, x times y. From the top equation, x equals 2,000 minus 2y. Then plug that in there. So we have 2,000 minus 2y times y equals a max. And then hit this with well, no, first do the algebra. So 2,000y minus 2y squared equals a max. And now is the time for us to do the Ddy derivative. And we have 2,000 minus 4y equals 0. $2,000 equals 4y. Y equals 500. And if y is equal to 500, then x is 1,000. Right? You will take this now, plug over there, and you will have that x is equal to 2,000 minus 2 times 500, which is 1,000. So now the plot of land is 1,000 yard by 500 yard. So you see that it's not a square. The previous one was a square, but now we have a rectangle, 1,000 by 500. And so guys, this is a procedure that guarantees maximum area. Next configuration? Sure, why not, right? Say farmer has to separate things. Cabbage, rabbits, and tigers. There you go. Can't put these things together, right? So we have now 3 bins. One for cabbage, one for rabbits, and one for tigers. I would think that all of the rabbits will be hanging out right there. And the tigers will be all hanging out right here. That's what I think. I might be wrong, but yeah. And the cabbage will be hanging out wherever you put it, right? Because the cabbage really can't move. All right, so clearly we have to separate these things. Now, we don't care about that. We're just going to look at the geometry of this. How many x's, how many y's, what do I have? These divisions are now fence, right? You got to put the fence between the cabbage and tigers and rabbits, otherwise not good. 4 y's, there we go. So that just changes your constraint equation. Your area equation, x times y, stays the same. You want the maximum plot. right? So now I have 2x plus 4y for 2,000 yard of fence, and xy still a max. So from the top equation, divide by 2 first. We have x plus 2y equal 1,000. And then solve for x, 1,000 minus 2y. Then plug in. And we have, instead of x, we have 1,000 minus 2y times y equals a max. And then 1,000y minus 2y squared is a max. And we hit this with a derivative, ddy. So that's 1,000 minus 4y equals 0. And hey, here we go. Y is 250 now. 250 yards. Plug in. X equals 1,000 minus 2 times 250. And the answer is 500. So, what do I have? I have 500 by 250 yards. And then we have the other 2 fence parts that we have to put in the middle to separate, right? Cabbage and tigers and rabbits and whatever I had. Does it make sense?
That's the outer boundary?
The outer dimensions, yeah. We came up with x, which is this distance. X is 500, and we came up with a y. Y is 250, which is the height. So it's 500 times 250, and you have this one for 250 and this one for 250. So now think about it. 500 plus 500 is 1,000. 250, 250, 250, 250. Another 1,000, 1,000 plus 1,000, 2,000 of fence available. So calculus does these things for us, and as a farmer, now we know how to fence these things off. Now, it doesn't matter that, crazy configuration that you can get. Now you can get anything. As long as you're able to account for all of the black lines, which is the fence, you should be able to set up equations. So maybe you want to do that, right? And give rabbits a lot of place to hop, and then there's a cabbage over here, right? So that's possible as well. So that's x, that's y, and then over here, let's say x over 2, and y over 2, right? This geometry would clearly add to regular 2x plus 2y perimeter, because you have the perimeter fence on the outside. That's 2x plus 2y. It would add x over 2 for the top line inside plus y over 2, and that's equal to 2,000, right? So it doesn't really matter. Your xy is still max, right? This will return different values for x and a y, because you have now some fence that you have to save for the inside. So there's a lot of these calculations that you can do. Some other problems, mainly geometry. For instance, we talked about packaging engineering, right? And let's say you want to send golf balls across the country or world or whatever, right? Now, golf balls are pretty small, right? And you just want to send a certain volume because isn't it that each golf ball has a certain volume? So you can multiply that volume times, let's say, 1,000 if you want to send 1,000 golf balls. The shape of the box really doesn't matter, right? Because you just need that amount of area because golf balls are going to arrange itself and follow, right, the structure of the box. It's not that you're shipping a car and you can't, right? So in certain cases, the shape of the box, the dimensions of the box are not important, right? Because whatever you are plugging in, it's just a lot of loose single units so they can distribute to take the shape of the box. You can't really do that with a projector, right? Because the projector has the volume, but it also has a sturdy shape. And yeah, so packaging engineering is a very interesting area where you have to take in account a lot of these things. But one of the objective functions over there is that you must minimize the surface area of the box because minimizing surface area of the box saves money on material for the box. Times 10,000 boxes, 100,000 boxes, million boxes, what you are going to get is big savings, right, on that amount of boxes. So let's say that you are constructing, so construct a box with square base and volume of, let's say, 60 inches cubed. Find dimensions so that surface area is minimum. So construct a box. Guys, you get to go home, take scissors, and make this. All right? It is as simple. If you're interested in these things, you compute this thing and you actually build it. And if you build it from a material that can sustain, you can actually measure the volume as well, because you can pour the water in if you are not making it a paper, but something you glue it and whatever, right? Math Club did these kind of things in the lab 6 years ago, 7 years ago. We went to chemistry lab and we did just fun projects with related rates and optimization. You can do a lot, right? You take a piece of dry ice and you watch it melt and you measure the rates and then you plot and everything, and it's just perfect because all of these things, they're just explaining the world around you. That's the relevance. So now we know what the box looks like. So this is the box. The problem says square base. That means that we are allowed to use a different measurement for the height. But it's a square base. So now, what do I have? If I have a square base and I have 6 sides, I know that the volume equation is the constraint because I have the volume given, 60 inches cubed. So x times y is 60. So x squared y is 60. The common sense that we have to employ here is the fact that the box is three-dimensional, so I need the height times the width times the length or whatever, right? So three units. So we have x times x for area of the base times the height. That's the y. So x squared y, that's your constraint equation. What's the objective equation? What am I minimizing? What am I minimizing? Surface area. So what is the surface area for the box? Is that area of each of the faces? How many faces of the box I have? 6. So what is the top and bottom faces? What is the area of those? X squared, and I have 2 of those, right? I have x squared on the bottom for area and x squared on the top for area. How about on the sides? X, y, and how many of those I have? Yeah. And we want that to be minimum. There is your objective equation. So the top equation, the first equation, is the volume equation. And then the one on the bottom is the objective equation. So now, when I put all of these things together, I am working with x squared y equals 60 and 2x squared plus 4xy equals minimum. Now there is a little bit of finesse of how to solve this, right? Observe that at the bottom you only have a single y. So you solve for y. And y is 60 over x squared. And you plug that in. So 2x squared plus 4 times x times 60 over x squared equals to minimum. And cancel one of these x's. We get 2x squared plus 4 times 60 is 240 over x equals the minimum. And there it is. I have a single equation. I have a single equation which only contains x, and that's the time when I hit it with a derivative. So what do I do? Well, just take the derivative. It's 4x minus 240 over x squared equals to 0. The second derivative over there, the 240 over x, you don't do the quotient rule on that. That's just x to the minus 1. And the derivative of x to the minus 1 is minus 1 times x to the minus 2, which is minus 1 over x squared times 240. All you need to do here is to solve the problem. And the way we solve this problem is multiply through by x squared to kill the fraction. We get 4x cubed minus 240 equal to 0. 4x cubed equal to 240. X cubed equal to 60. And finally, x is cube root of 60. Now you can go on and figure out what, you know. Now there is a formula for y. Y is 60 over cube root of 60 squared, which obviously works out to be cube root of 60. So it's a cube. Cube root of 60 by cube root of 60 by cube root of 60. These dimensions, if you have a cube, a box that is a cube, it has the minimum surface area. So you've seen that for a rectangle, if you are trying to maximize area for the 2D objects, you get a square. And now you see that if you're trying to minimize surface area for 3D objects, you get a cube. So there's always this game of like the perfect object, right? Unless you mess with dimensions. You say, create a box, but no top. All right? You're going to use some kind of lid or some other mechanism to seal the box. So you say a box with a square base and no top, right? No top means it changes the equations, because no top and top was x squared and the bottom was x squared, right? That's the 2x squared. So if I say no top, then this 2 is not in the equation anymore, because you only have the bottom x squared, you do not have top x squared. If I said no top. We have to be careful a little bit, with the wording and what's wanted, right? Because you just modify these problems a little bit here and there. The book contains a problem for like post office and so on, the airport, when they say that the girth of the package, right, or luggage has to be a certain amount, right? And they want to have the minimum or the maximum volume and stuff like that. So there are many combinations here.
So is the constraint the one with the bottom x squared?
Constraint is always what's given to you as a number. So in this case, the volume was given 60 cubes. So that's the constraint. And the objective is only the one, always the one with min and max in it, because that's what you are trying to figure out. Yeah. So x squared y equals 60 is the constraint. You are working within those constraints. Your box must have 60 inches cubed, right? So that's a constraint. Would you agree? Otherwise, you're creating any box. But I'm imposing constraint on you. It must have 60 inches cubed. So that's a constraint for your... They have a very interesting problem in a book, which I haven't... I didn't open the book yet, so... Give me a second. Seems that both sides of the classroom in the last row has way too much fun. I'll have to pick up some more interesting problems, I guess. Make this much spicier, because obviously they're bored with such easy concepts that I'm presenting over here. All right. So the next problem is the flower garden, but we are actually going to do business application for this as soon as we're done with the problem. So what we have is the flower garden surrounded by either grass or brick patio, concrete, whatever, right? So the flower garden is inside, and I think it's a grass. Whatever. So we'll put the flowers over here, and we'll do the grass around. Good. Well, thank you. I worked very hard. Now, these dimensions are 2 meters each. If you don't know what meters are, I am 2 meters tall, so there you go. It's about 6 feet. So they say that a rectangular flower garden with area of 30 meters squared. So 30 meters squared is in the middle over here, and we have x and a y for the inner garden. So the inner rectangle, like this, with x and a y, has 30 meters squared, and that's the middle. And then you have the stuff around. Great. So what's my constraint equation? If I know there is 30 meters squared of the area inside, what do I write? What happened?
Well, what are you trying to find out? The grass part?
I'm trying to find the dimensions of the garden here and here. You can call them A and B if you want to see what, because I have all these specs that have to be followed. I need to have 30 meters square in the middle, and then I have to have plus 2 meters on each side and plus 1 meter top and bottom. So what are the dimensions of A and B?
So why does flower garden matter?
It matters because we want to minimize the combined area.
Can I try?
What do you mean, can I try?
Can I try?
Yeah, what's going on?
1,000 again.
Yeah, please do.
X, Y, max, and then x squared plus y squared equals 30. Yeah.
Nope.
Thank you. Appreciate that.
So, what is the constraint equation? What do I have? What do I have? So, what do I have? Guys, what's obvious as an equation that I have to write? xy equals 30. Thank you. Holy nightmare. xy equals 30. That's obvious because you have the area for the rectangle that you know it's 30. We shouldn't be thinking about that. It's done, right? xy equals 30. Now we have to start thinking. What is the length for A? How long is A? Look at the diagram. No, area. This is area. This 30 is not a length, so don't look at that. What's the length across for A?
X plus 4.
X plus 4. Great. We have the unknown area, unknown length in here, plus 2 on each side, so it's plus 4. And what's B? Y plus 2. Very good. So now what do I want? I want to create the minimum area, but area is AB, so I have x plus 4 times y plus 2 is equal to minimum. And xy is 30. There's the set. Solve for whichever one you want. I don't know, x equals 30 over y. Doesn't matter. Plug in. X plus 4 times, no. 30 over y plus 4 times y plus 2 equals min. FOIL 30 plus 4y plus 60 over y plus 8 equals min. Yeah, we can do 30 plus 8, 38, but doesn't matter because when we hit it with the derivative, they both die as constants. So derivative of 30 is 0. 4 minus 60 over y squared equals to 0. Times y squared everywhere. Four y squared minus 60 equals 0. Y squared equals 15. Y equals square root of 15. Plug in. X equals 30 over square root of 15. Rationalize. We don't like square root of 15 in denominator. And we get 30 root 15 over 15. Now this cancels. And there we go. So X is 2 root 15 by root 15 meters. So those are the dimensions. Not a square, right? But if you use these dimensions for the outer side of your garden, you are going to have minimum area for the combined garden, while the middle area of the garden will be... Oh, wait. No, it's wrong. These are X and a Y. We are looking for A and B. So A is X plus 4. So that's 2 root 15 plus 4. And B is Y plus 2, which is root 15 plus 2. So dimensions are 2 root 15 plus 4 by root 15 plus 2 meters. So those are the dimensions. Now you go and you get your decimals for root 15, right? Like 3.9 or whatever, and then you go from there. Now, where do you actually use this to make money? Right? What do you need to optimize? What do you need to reduce the surface area of, but keep the area of the middle so that you can, for business purposes, reduce the cost and keep most money for profit? Any ideas? The shape of the swimming pool is important because it's the Olympic thing, right? So you have to have, it's not just the surface area of the pool, but unless it's synchronized swimming. All right. This? Yeah, this is called Something is Dying. This is called book. You don't know. So, do you see that there is a white border around each page called margins? Yeah. Now that's your flower garden with the grass, which is 1 meter and 2 meters, right? So you are minimizing the overall area, meaning you are making the paper as small as possible. That book has 1,000 pages, right? So if you shave off 1 cent of each page times 1,000 pages, you are saving $10 on a print. Times 10,000 books is $100,000. So if this calculation can save $100,000 per book, you're making your money as a person who does this for the publisher, right? You ever wondered why all the books are different sizes? Think it's random? No, it's not random. Right? So, the flower garden, which is garbage problem, no one cares, right? You just go and say, this looks good, right? You hire a person to come in and they just say, all right, we planned these 6 plants over here for $10,000, you're done, right? No one cares about garden problem. Now is the time for you to take this problem and think, okay, right? These are the things. What else can you do with these problems? Well, you didn't have to pick your medical insurance plans, right? But maybe you have, and you have options. So that could be done, and a lot of other stuff. Let me give you another consulting thing that, you know, people get hired. I mean, those of us who know how to do this. So, say, I don't have time to compute all of the details for it, but if you are business-oriented, here is your Calculus 101 making money kind of situation. In these calculations, you should be saving hundreds of thousands of dollars to this company, and it's not a problem for you to be paid like 30K or something for this, you know, 15 minutes calculation. So you can be making serious money. Now see, you might know how to do this and learn in class how to do this, but then that other aspect of you actually doing the write-up and presentation, and that's the project, right? So if you can't present it, well, someone else will, and you don't get to eat. So it's very important for you to take the communications class and writing classes and technical writing classes and all of these kind of things to supplement your knowledge of calculus and engineering so that you are actually useful in the workforce. And you can present ideas and yourself and be employed and all of that stuff. So here's a shore. Here's the sea. And here's the oil rig. And here's the refinery R. And you have pipes. Now, it should be common sense that if this rig is reasonably close, you should lay the pipes rather than have a tanker go back and forth for 2 miles or something, right? You can't even, I think you can't even stop the tanker in that much. So you're going to run some pipes. Now, the issue with building a pipeline is that pipes that are built underwater and pipes that are done on land are different cost, right? Because it's a different technology and much harder to set up pipes underwater. So I really don't know exact numbers, but we can make up anything. It will serve the purpose for the problem. So what are the 3 options that you can take? You see, common sense will tell you that you might want to run the pipe all the way to the shore and then 90 degrees underwater, because that's the shortest distance for the very expensive pipe. So this path 1 gives you the shortest distance for the most expensive pipe, but it gives you the longest distance for the least expensive pipe. The other option for you is to run the pipe diagonal. Now, all of this pipe is underwater, right? So you are only using the very expensive pipe, and you are not using any ground pipe at all. So which one is going to win? You are looking at this and you say, okay, the distance 1 is much shorter underwater than distance 2. So it seems that the number 2 would be the winner. But what I'm going to tell you now is that both of those are not optimal ways to do it. The most optimal way to do this is to run pipe for some length here and then go on the angle like that. And at that point you will say, well, how far do I have to run it? Now, if you are able to do this calculation and figure out this x, that's where your $30,000 payment is that you can score in 15 minutes of calculations, right? Because the oil company, which is made out of money, is going to save few $100,000 on this thing, and it's nothing for them to give you 30K, which is petty cash, right? Here you go, right? It's like, you know, little Timmy, here for your efforts, right? Please, right? Don't let the door hit you on your way out. So if you are able to run this calculation, you can save all that money. Now let's just set up some scenario, and then if you are interested, you will complete the problem. So let's say that this distance over here is, I don't know, 5 miles. And let's say that this distance over here is 2 miles. Now let's say those are the distances. Pick anything. What would be the price of pipe above ground? Right? What would be the price? Let's set something like per mile. 100,000? Okay. So 100,000, 1 mile on ground. And what is the price for underwater for 1 mile? 200,000, double? Should be more, but that's okay. 200 is fine. 1 mile under the sea. Yeah. There you go. I have an unknown distance x, which is the distance for the pipe on the ground. And then I can set up this to be, let's say, y for the distance there. What am I trying to minimize here? I'm not trying to minimize the length. I'm trying to minimize cost. They're the business people right there in the corner. I'm trying to minimize cost of the pipe. So what do I have? I have the cost of the pipe, which is 100K times X. So this is the cost of the pipe above ground, plus cost of the pipe, 200,000 times Y under C needs to be minimum. That's what I'm trying to minimize. I want to minimize the cost of the pipe, price of the pipe. So this part is ground, this part is C, and both of those are cost, and I want to minimize the cost. So that's that. So there's your objective equation. And now we just have to figure out the constraint. And the constraint is clearly the geometry, which is this, this triangle over here. Right? You have a triangle here. And this triangle is a simple Pythagorean theorem, and you have all the dimensions of this triangle in terms of x and y. So that's your constraint. So what are the sides for this triangle? Okay, let's draw the triangle on a side. You have y, you have 2, and hopefully you understand that this is 5 minus x, right? If the entire distance from top to bottom is 5, and the red part is x, which is what you're not using, then 5 minus x is over there. So Just do the Pythagorean theorem for it. Y squared is equal to 5 minus x squared plus 4, right, which is 2 squared. And there's your constraint equation. So what are we having? We're having 100,000 x plus 200,000 y equals minimum. And we have y squared is equal to 25 minus 10x plus x squared, and then plus 4 will make this into 29. There they are. You know what to do. Square root both sides. Get y equals the square root of blah blah. Plug that square root in the other equation. Hit it with the derivative. Good luck. And there's your x. Bring that x back here to find y, and you have the amount of pipe on the ground, amount of pipe on the water. You can compute the cost. And you can compute the cost of path 1 and path 2 and see that your cost is lower. So when I make these numbers up and so on, sometimes I run into, saving $300,000, sometimes say $500,000, sometimes, depending on which numbers I pick. But what you see there in that box, those two equations, once you solve, they guarantee the lowest cost for the pipe. And if you have the lowest cost for the pipe, right, then that means you're saving all the money. So whoever was the one who solved it is the little something for you, like 30, 40, 50K, and go buy a Tesla. Or cat food, I don't know. People are different things. 30K cat food? It's a life supply. Expiration date on that thing. At least the cat will be fat and happy for a long time. When you come back from the break, we are going to do some linearization. That's it. I hope you're not disappointed.